All right. Oh, sorry. Thank you. Okay. Thank you. Appreciate it. So there we go. So yeah, we talked about adding things up in parallel and anti-parallel. So if you add them up anti-parallel, you basically just subtract them. So 5 minus 3 is 2 with those vectors. That's what's nice about adding up vectors in just one dimension. You could just use algebra, right? Or arithmetic, basically. Positive, negative, and just there you go. Then we talked about it's not always as easy, right? Because now if I have vector C, which points to the right, vector D points up, I can't just add them up algebraically anymore. I got to use a little bit of trigonometry, or in this case we use a little bit of Pythagorean theorem. But that just got us the magnitude of the vector phi. In order to get direction, we need to specify with an angle, or something like that. This is only the magnitude of the vector, so the direction of the vector is right there, where the total vector can be expressed like that. Again, those of you who took regular physics or AP physics, you know that, and that's how we always express this. And now I'm introducing to you this idea of bracket notation right here, which is based now, these are sharp brackets. They're like that. They go, even though Khan Academy does otherwise, they should be like this to suggest a vector, because if you're using the parentheses notation, that suggests a point. Okay? So vectors uses the bracket notation. And so, like, here's a vector A. Vector A has is going to be in 3 spatial dimensions. So it's got an x component, a y component, and a z component. But we're dealing with this vector here, which is vector r. I'm using it because it's basically, it's going to be easier math on us because it's a 3, 4, 5 triangle. But basically, you can say vector r, well, that's the x component of vector r. That's how much vector r goes in the x direction. And then there's the y component of vector r. That's how much it goes in the y direction. And then they add up. If you add those up, you get the actual vector r. So this is a way to describe vector r, 3, 4. And if the unit was a displacement or something, or position, we could say meters. And those meters is essentially, it's a unit, it's a scalar quantity, and it can distribute into that vector right there. Okay, and then there's also this notation. You'll see a lot more on your in your textbook. I prefer the bracket notation over this notation, but sometimes this is easier. So, and basically that's basically taking, you got a scalar quantity of how much is there times I hat. This is a unit vector. It has a magnitude equal to 1. And ij, thank you guys. So to unscrew the red ones, I would use this. And basically you want to put in like a weak battery and like this thing is basically a dead battery. And it should still work. Yeah. And just the red ones get those. All the other blue ones should stay the same. Please. Thank you. So, yes, ijk, they're unit vectors, and they point in the direction of, so I points in the direction of the, I tend to use x, y, z. That's the way I was trained to do it, and I just like it better. ijk just gives me more, makes me have to think more. Which one's I? Is it a long x? Oh, I don't know. So x hat I like because yeah, it is a unit of 1, just 1, not no units or anything like that. So it's got a magnitude of 1, and it just points in a direction. So if you use ijk, I hat, which does Matthew use ijk? I would assume people have done it. Yeah. So okay, if you're used to that, that's totally fine. I points in the x direction, j points in the y direction, and k points in the z direction. So I think even math flips these axes around, does all sorts of fun stuff. But yeah, so yeah, that's the hat notation right there. And then, but there's also, so that's a unit vector that's along the axis there. That's along the axis. And I do have a fun little Python program, which I'm trying to get more lessons with Python and coding and things like that. So I'm just kind of like messing around with some of this stuff. Because what's cool about it what's cool about things like Python is they use like physics functions and equations, and then you can change those equations and see how it, and then run the program and see how it materializes. So this one's the 3D vector. So you can kind of see like here's an axis. This could be like x hat, y hat, z hat right there. And then if you scale them up with some scalar component, they can blow up and then add up to create your actual vector. So here's the actual vector in space, and then you can even like you can even zoom in. It's all sorts of fun things. So it kind of shows how you can rotate your axis around. And notice the vector, we're looking at it in different ways, but the vector remains its same magnitude and same, typically it would be same direction. You're not really seeing that here, but okay. So, and I'm going to try to use more because there's a lot of cool stuff that thing shows. Okay, so the other thing though that we could write is that another way we could express this vector is to say it's the magnitude, not r, we're using baby r. So it's the magnitude of the vector multiplied by r hat. So r hat is also a vector. So this is another way to, I'm giving you all these ways to write this. It's up to you about it. We're going to use this later. I'm going to just kind of throw it in here, but then we're not gonna really use this until the last unit, because this does some really clever things. This does some really clever things with, especially with the gravitational force, and you'll be able to see with the electric force too. It does the same thing. So okay, r hat is a vector equal to 1, but unlike x hat, y hat, and z hat, where these aren't equal to 1 as well, but this goes along the x direction, this goes along the y direction, and this goes along the z direction. R hat goes whatever direction the vector is pointing, and it's just equal to 1. So, for example, if I had a vector, and it's hard to draw it in 3D space, if I had a vector like that, that could be r hat. But when I multiply the magnitude of r to r hat, it scales it up so that it's now the actual vector r.
Wait, what? Isn't r hat just 1?
R hat is just 1, but if I multiply it by a scalar quantity, it blows it up or shrinks it or does whatever that thing is going to do. We'll try with numbers. Let me know about so because we got vector r, right? Vector r is 3, 4, right?
Yeah.
And vector r, it could also be described as the magnitude of r multiplied by r. So this is using our triangle from before. Yes, so just make sure everybody, yeah. This is a triangle from before. It's got a magnitude of 5, it's 3, 4, 5 triangle. So 3, 4, and then this I could express as r hat, and I'm going to go figure out what r hat is. So r is just 5. So I can divide both sides by 5. And now this 5 divides here and divides here, right? Just like the multiplier would go in there. So 3 divided by 5 in decimal form is 0.6, comma 0.8. 4 divided by 5 is 0.8. So r hat is a vector, no units, that is equal to 0.6, 0.8, comma 0.8. So it's pointing somewhere in space, 0.6, so let's say this is my axis right here. It's pointing 0.6 this way and 0.8 that way, so it points like this. So r hat is x hat has to point along the x-axis. Y hat has to point along the y-axis. R hat can point anywhere it darn well chooses, right? It just it doesn't have to obey that, but it still needs to be a unitless vector that that adds up to 1. So we can check to see if this thing adds up to 1, because if I take the magnitude of r hat and square it, it's going to obey Pythagorean theorem. So 0.6 squared is 0.36. 0.8 squared is 0.64. And those add up to 1. Square root of 1 is 1. So r hat does have a magnitude of 1. Whoa. Uh-oh. There's lag? Bummer.
Let's just give up.
The internet is trash.
It's the school's
So info, what? Looks like it's coming back. Let's see. Let's try it. Technical difficulties, sorry. You can just fast forward through this. I'm not editing any of this. No, you guys fast forward. It's been like for some reason like it'll cut and then make another video, so I'll have like 2 videos that I'll need to combine. I'm hitting a point where I'm getting so lazy, I'm just like, I might just throw the 2 videos on YouTube. It's gonna be easier on me.
Part 1, part 2.
Oh, really? I wonder if I could override that.
More ad revenue for you.
Well, right now they're unlisted, so I'm not getting any of
Wait, they gotta be over 10 minutes. You monetize.
I know, you make it public, make it a great
Alright, we're back!
I am from England.
Okay!
I know, make it 10%.
Yeah, it's got a magnitude vector. The r hat has a magnitude equal to 1, and it's pointing in some random direction. It's 0.6, 0.8. We can make it 3D, we can do all sorts of things, but that's that particular vector. Now, so going back to that definition then, so going back to r vector is the magnitude of r multiplied by r hat. Or you could just go back in reverse. So r hat is a vector equal to 1, pointing in space, right? With me? Okay? And then if I multiply that though by its scalar factor, by this scalar right up here, which is just the magnitude. In fact, I think I could be wrong, but I think that's why scalars are called scalars, because they scale up or scale down a vector.
Like, comment, subscribe.
So this is going to multiply. This is going to multiply out, right? And then 5 times 0.6 is 3. Comma, and then 5 times 0.8 is 4. So I get the actual vector back. So in other words, this is just another way to describe that vector. Does that make it a little more?
It's just a unit vector.
Yeah.
Okay.
It is a unit vector, but an r hat can point wherever the heck it wants. And I think it's on your equation sheet, the r hat notation. I will be honest though, I've never seen r hat, x hat, or any I hat, on the AP exam itself. But if you take the, if you, I'll say when you take this exam and you pass it, and you decide you don't want to take physics, mechanics, you're going to take E&M next year, they're going to expect that you know what a hat notation is. So that's one of the reasons.
I thought they were changing the physics C test this year.
They are?
Yeah, they're changing it, they said. They said they're like more conceptual now.
Oh, okay, I'll check that out. Thank you. All right. So here we go. Questions, comments, concerns here before I move on to the next idea, which is components. All right.
Like, dislike, comment, share with friends. Guys, remember to press that big bell button so you hit the notifications. Remember to subscribe to the content.
Now I got vectors E and F.
Oh, no.
Yeah, oh no.
Oh, Schleich.
And I want to add these up. I already vector E, E and F, ugh, yeah, gross, right? How the heck, right? Well, graphically this ain't that bad though. Graphically, because how do you add up vectors graphically? Head to tail. So if I want to add these up, I put the head of vector E attaching to the tail of vector F. So I got E, this is vector E plus vector F. And then I can get my ruler out. Whoops. Something like that. And there's, so there, again, I'll call it my R vector. So my R vector points that way. So if I scaled appropriately, I could use my ruler then, find out how big that is, and then use that, and graphically I could do it. And then I would need a protractor or something to figure out that angle to describe that vector. So that's one way you could do it, graphically. The other way, though, is analytically. So analytically, though, I don't have any algebra, I don't got any maths that I know that can add up 6 and 8 in those spatial dimensions that don't help me. So the idea here, the trick that we're going to do is we are going to resolve these vectors into their components. We're going to break them up and explain them by their components, and then use their components to do what we used to in the past, which is adding up things horizontally or vertically. So let me show you exactly what I mean by that. So first thing I'm going to do is, here's vector E. Vector E I'm going to split up. Here's EX. Here's EY. So this is called resolving a vector into its components. I'm splitting it up so that EX points this way, and then EY points that way. And then I'll resolve vector F as well. And then vector, so vector F, boom, 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 boom. So this is Fy, this is Fx. Move this one a little further. So formally kind of defining these components. So these are components. This is the x component of vector E. This is the y component of vector E. And this is the x component of vector F. This is the y component of vector F. So I'm going to kind of go over here this definition. What I did just now is I resolved those vectors into their components. And vector components, by definition, are pretty much two perpendicular vectors. So they don't have to be two. There could be a third vector now as well. But they're vectors that are perpendicular to each other, but they're parallel to the horizontal axis and the vertical axis. They're like x hat, y hat, z hat, except just scaled up. So they add up to get the main vector. So these components add up to get the original vector of what you just broke apart. And I see people writing, so I'll pause for a moment here. In fact, I'll set up for the next. that's what we're gonna do next.
Stop yourself.
Yes. So, okay, what I want you guys to do right now. Yeah, don't go into the law of cosines or any kind of that nonsense right there. So by using some simple trigonometry, what I want you to do, let's split this class. Let's split it like let's split it like this. So this half over here, you guys are gonna do. You guys are gonna get fx, or you're gonna get fx and fy. This side over here, you guys are gonna get ex and ey. So go ahead and calculate them. You know the angle is 60 for f, and you know the hypotenuse, you know the angle is 30, you know the hypotenuse, you should be able to calculate just using a simple trick, yeah. I think so. I think so. Mm-hmm. That's right.
Oh, you still doing math last year?
Oh my god, you're right.
Isn't that so much easier with the bracket notation?
Well, we learned it in math last year, but we did not teach it very well. Hey, even if you watched it, he'd say, yeah, probably.
Does anyone need more time calculating this? Raise your hand if you need more time. Okay, give me more time.
Alright, nice.
Okay, so we're trying to get involved.
Yeah, basically.
Okay, because we're kind of confused on are we supposed to
Oh, yeah, so those are probably like either fresh or like or Amazon ones. So they're going slow. So you might want Alright, so let's see. Anusha, you did E, right? So what trig function did you use to get EY? Yeah, I would agree. Sine of theta equals what over what? Yeah, the opposite would be EY, right? Yeah, EY. So it's going to be EY divided by, and I'm just going to kind of write down the general equation right now, divided by the magnitude of the E vector, right? So we can then solve for this. You'll get theta equals sine of the inverse, and then EY. Oh, wait, I don't want that. I know theta. Don't. So E multiplied by sine of theta equals EY. The E vector is 6. Sine of 30 and EY, and what did you get?
No, because you know how it's
3. Yeah.
That's basically the x thing, right? So sine, so what's the hypotenuse? Sine theta times is equal to I didn't do that.
And then E as well. So Ethan,
I decided 60.
what did you use for
And then you remind me
what did you use for EX? Yeah, so it's cosine theta, that's going to be EX over the magnitude of E. So you get E cosine theta equal, well, this is basically 6, so 6 cosine of 30. And then what did you get for EX, Ethan? 5.2? Sounds good. So there we go. We got now our components for EX and EY. And what's nice is now I can express this vector as 5.2 comma 3. in bracket notation. Whoa. So it's pretty much the same process for F, so I'm just going to ask what you guys got. So people who did F, what did you get for Fx? So Isaac, what did you get for Fx? 4, yeah. So using the same method right there. And then for Fy, Krish, what did you get for Fy?
4.
In decimal form.
Really?
What was it? 6.92, thank you. And then we can express that in bracket notation as well. Vector F is 4, comma 6.92. And now, to get our R vector, our resultant vector, we're adding up vector E plus vector F. So, that's basically going to be 5.2, comma 3 plus 4, comma 6.92. And so, yeah, is that though, is this the X component or Y component of vector E? That's the X. What about this one? This is the X. This one's the Y. So we're going to add up the X's and add up the Y's together. And then I'll explain to you why we're even doing that. So go ahead and do that, if you haven't done so already.
Oh yeah? What are you gonna get? Dude, I'm trying to get spam soup.
Seems like people have already added it up. So what's 5.2 plus 4? 9.2. And then 3 plus 6.92? And so there, if I asked for the R vector, that's it. You're done. That's what's nice about that notation. That expresses the vector. But if we wanted to find the magnitude, what would I need to use? Pythagorean theorem, yeah, which is Rx squared plus Ry squared. So 9.2 squared plus 9.92 squared, and what's that end up being? 13.53. So the magnitude is 13.5. Whatever. So yeah. Questions here? What's that?
Do we need the angle?
No, that's what's so nice about that notation. We don't.
Oh, for magnitude.
Yeah, this is just the magnitude, I'm saying, yes. But if I did then say, what's the angle that it makes, with the horizontal or something, then you would need to go find the angle.
That's annoying.
Yeah. And again, often, I mean, you've worked with free body diagram stuff. Most of the time you have to find the angle to solve the problem, So, yeah.
If we find the angle, isn't it better to just do graphic?
And I mean, but then you gotta measure out with a ruler and things like that, and so. What's that? Yeah.
60 plus 90, and then you add whatever left over from the new.
No, 60 plus 90. No. I don't think so. I'll have to see you later. So, okay. So we're good? Yeah. We're all right. Oh, dang it. No. Sorry. I gotta explain why
Why you added?
Yeah, why we add them like that. So here is here again. We were adding up vector E plus vector F in order to get R, right? And what we did to do it analytically is we took vector E, resolved it into its components Ex and Ey. And then we broke up vector F in components Fx and Fy. So the reason this works is because, so as long as a vector has the same amount and is pointing in the same direction, it is the same vector. Okay? So all I'm going to do is move vector Ey and Fx. So I'll move that. Whoops, I want to make there.
But then you're gonna do that.
So, can you see the triangle?
Yes.
Whoa.
Like and subscribe, share with friends.
So, yeah, let's.
Video time, teacher goes crazy.
So this is all this stuff here. This is Rx, and all this stuff here. This is Ry. Right? So if you resolve the components and then add up the components in the horizontal direction and add up the components in the vertical direction, they get the components of the vector you're looking for. And that's why this works. That's why the magnitude, we had to use the Pythagorean theorem. Because literally, we've made a triangle. So you're forcing those right triangles and using that to solve the problem. In general, it's sine and cosine is used to find the vertical component. Cosine is used to find the horizontal component. But not always. I'd say 90% of the time it works that way, but there's 10% of the time where just you want to use trigonometry and just obey that. Stick to it. Questions there? Comments? Concerns? All right. So, perfect. The next thing we're going to do here involves people who've taken physics already. Keep your mouth shut.
Oh.
It's the street light problem.
I thought we're not allowed to bring that at school. Clickbait, teacher bring guns to school.
So what's going to happen, so what you're going to do, we're going to do this on the hallway in just a moment. So I got a dart, obviously, and you know, you just saw it fire. I've also got a penny, though, that's going to stay right here. So I'll do it without the dart so you can just see what happens. So if you, now you don't want to do it, like this, you don't want to fire like this, you want to be as completely horizontal as you can, because if you do that, the penny will just drop like that. So, what's going to happen? So again, horizontally, completely horizontally, maybe.
Exactly, we get it, Mr.
It's getting filmed.
So, it's forever immortalized. So yeah, you're firing completely horizontally, and so again, people taking physics, you're going to stay silent. But people who have not taken physics before, I want you to think about, I'm going to fire these, and so at the same time, the dart's going to fire and the penny's going to drop. The question I'm posing to you is, which one hits the ground first and why? That's the question. Which one hits the ground first and why do you think it? So take a moment to think about it for yourself and then share your justification with your table groups. So go ahead and do that right now. Go ahead. Oh, you're a physics.
I didn't know what I could get. Like, I only had to get.
You two are discussing which shorter distance to fall. Because it's going sideways, it has to take more time to fall.
All right, so instead of so hopefully you all shared. You want to commit to something, right? That's science. That's what you do. You just like. I mean, well, sometimes you do, but if you're doing science, you don't just kind of like do things just to do things. Sometimes you do to like give an idea, but basically you do what before you do an experiment? You have a hypothesis, right? You have a model of how this thing should work, right? And so by doing the experiment, you are putting your model to the test. You are saying in science we're constantly trying to disprove ourselves because then we're eliminating things that it's not, right? So you want to voice your hypothesis of what you think of what your model, how it describes. But so hopefully you've done that and committed to it. That's a good thing, because now the experiment is going to decide whether or not your hypothesis is supported or not supported. But what would be a good reason as to why the penny would hit the ground first?
Has more mass.
It's got more. The penny has more mass. Okay, that could be. So maybe it's got more mass, so it's going to hit the ground first.
It has a shorter distance to fall.
Oh, it's got a shorter distance to fall, right? This one's going to fall this far. This dart's going to go. How does this small gun go so fast? What would be a good reason that the dart would hit the ground first?
Faster initially.
Yeah.
The penny goes up before it goes down.
Hopefully it's not going to go up. If it does that, that's yeah. But I know what you're saying is that it sometimes they get that recoil thing. Yeah.
Maybe because there's a faster initial.
So yeah, this one the dart moves with a faster initial velocity, so it's moving faster. Faster things get to places sooner, right? So maybe that could be a good reason as to why it hits the ground first. So. Once again, people who haven't taken physics, you get to carry the guns. So you're gonna run? It's my turn. Get revenge. Yes, we got quite a number of projects. We're also gonna do a rock. For people using this one, the penny goes on top like this.
On top of the bullets.
Yeah. So again, you got to be really careful. So just Jackson.
Yeah.
Right. Just like Jackson said, you don't want the penny to go up. If it's doing that, then try it again.
But is that gonna influence the direction the penny drops? Isn't it gonna go slightly forward technically? If you're gonna do that?
Hopefully not. Okay, so I got two guns and pennies. Once again, if you haven't taken physics, go ahead and grab your guns. And go out in the hallway and test it out. Test it out.
It's a big deal. Other than
This is America.
This is America.